I'm Paul, and I'm accelerating the pace of innovation in nuclear science and engineering with the OpenMC Monte Carlo code. So the Monte Carlo method is a generic method that's applied to many different areas. The very simple example that is, if you wanted to find the area of a circle, one approach that you could do is to basically draw a square around it and throw darts at that square. And if you count up the number of darts that go in the circle versus just in the square itself, you could figure out what is the area of the circle without knowing any math at all. You could just count them up. So that's effectively what the Monte Carlo method is. You're taking some system and repeating this trial experiment over and over, and eventually you infer something about the average behavior of the system. So in our case, rather than throwing darts at a circle, we're simulating neutrons as they're moving around a system, and that tells us what the average behavior of the neutrons would be, which is akin to solving the equation in the first place. OpenMC came into existence when I was doing my PhD thesis at MIT. We were really interested in studying Monte Carlo methods and what the scalability limitations were of these codes. Monte Carlo methods for particle transport are very computationally expensive, and so we're always looking at ways of making these faster and more efficient. So a lot of our work revolves around the use of these codes on high-performance computing architectures and how we can make them faster there. The underlying computer architectures are actually changing. So one of the big shifts that we've had in recent years is that nowadays a lot more science is being conducted on GPUs, and the programming models there are completely different than what we have for CPUs. And so unfortunately, you can't just take a code off the shelf and say, let me throw it onto the GPU and everything just works great. It actually takes a long sustained effort to get it running on GPUs. My work basically sits at the intersection of nuclear science and engineering and high-performance computing. And so there are some aspects of it that involve understanding the underlying physics of nuclear engineering, but also working with very large supercomputers and how to perform these simulations on large computers, including Aurora here at Argonne, as well as Frontier at Oak Ridge. Because we're sort of living at the bleeding edge here of high-performance computing, everything is new. The hardware is new, the software is new, compilers are new. With the effort that we've spent on it and all the investments that we've made through the exascale computing project, we've gotten to the point now where we actually have codes that are going to be working well on these supercomputers in the future. One of the things with nuclear reactors and other nuclear systems is that to actually go ahead and build them, they tend to be very expensive. And so to the extent possible, we try to do everything with simulation ahead of time, particularly for things that just haven't been built before and there's no experimental data. We're looking to make these systems safer, more economical. I think computational science really plays a huge role in making sure that we can design systems that meet those goals. That's very much a team pursuit, which I think is one of the things that the national laboratories very much excel at. This includes both staff members here at Argonne, includes postdocs, students, but also external collaborators as well. And so there's really a whole community built around developing this software. The impact of computational science on society is really that all of us here as scientists and engineers, we're trying to work on these very challenging problems that contribute to climate change and ultimately are going to help us produce energy in the future in a way that's sustainable, clean, economical. Computational science really plays a huge role there in basically allowing us to do these experiments that allow us to better understand the physical phenomena that underpin these systems. And so that's where I think as we look to the future, there's going to be more reliance on modeling and simulation and high-performance computing to really supplant experimentation if we can really understand the basic laws of physics through computational simulations. So I think if you're interested, definitely reach out to us. We love hearing from folks from all around the world and love working with new collaborators. So definitely reach out to us.